Dear colleagues, the topic of my talk is propagation of optical vortices in the system of twisted anisotropic and multi-helical optical fibers. This research is carried out in collaboration with my co-authors at Physical Technical Institute of Crimean Federal University. I'm going to stick to this content, so let me first briefly focus on motivation. Optical vortices are characterized by helicoidal shape of the wavefront with indefiniteness of the phase that leads to the appearance of an orbital angular momentum. Such unique properties make them promising carriers of information. Indeed, an additional orbital degree of freedom allows one to encode substantially more data as compared to the standard techniques. A successful application of optical vortices in information technologies naturally requires the means for controllable transformation of orbital angular momentum, which is necessary for performing the basic set of logic operations. Previous investigations have shown that some types of optical fibers, in particular twisted anisotropic and multi-helical fibers, possess specific properties that make them friendly medium for vortex transmission and control. In this context, it seems natural to assume that the systems constructed from these types of optical fibers may also have interesting capabilities. Therefore, in this work, we study the vortex propagation in the system of a twisted anisotropic and two multi-helical optical fibers. Here, considering a model of these fibers connected to each other is shown. Such a system we call as a sandwich MAM. Tensors of dielectric permittivities both of multi-helical and twisted anisotropic fibers are given in the slide, where the first term is the permittivity of an ideal fiber, the second term, an equation for multi-helical fiber on the left, describes the multi-helical permittivity profile having tau-fold rotational symmetry with respect to the fiber axis, and in the right-hand equation for an anisotropic fiber, the second term describes the effect of material anisotropy. Last term is caused by torsional mechanical stress induced by the twisting via the photoelastic effect. Also, we imply that these fibers are step indexed in weakly guidance region, and anisotropy axis of fibers coincide at the boundary. Circular polarized optical vortices with a topological charge more than 2 are known to be higher order aging modes of both multi-helical and anisotropic fibers with weakly anisotropy effect, or equivalently at a given condition. However, a certain twist pitch age, due to the degeneracy, the effect of small anisotropy can lead to the new structure of modes. So, we assume that fibers in sandwich are in the resonance region. Please note at the left-hand side, new hybrid modes of the multi-helical fiber are the superposition of optical vortices with the same polarization state and different topological charges, but modes for in twisted anisotropic fiber are formed by the orthogonal optical vortices with the same topological charge. Later circular polarized optical vortex is on the input end of the sandwich MAM. It leads to the exciting of certain fields in each fiber, which are expressed by the superposition of resonance modes of corresponding fiber. Also, one can write an expression for the field as the decomposition on optical vortices. At that, the partial energy of each optical vortex is determined from decomposition coefficients, which are obtained from boundary conditions. For example, I'm going to show transformation of input optical vortices of topological charge equals plus or minus 2. Here, the dependence of partial energy on the length of the first multi-helical fibers. Also, in the second row, angular momenta of the field in the first fiber are depicted. At certain length, 15.3 centimeter here, incident right-hand polarized optical vortex is transformed to an optical vortex of opposite topological charge. Left-hand circular polarized optical vortices, being agent fields of the multi-helical fiber, remain unchanged. So, if length of the first fiber is 15.3 centimeter, then in the second anisotropic fiber, we obtain following. Here, uncommon optical vortex of topological charge equals 2 can be transformed to the one with orthogonal polarization state. Maximum efficiency is achieved when the length of the fiber is 11.7 centimeter. Finally, here we have total transformation in the sandwich MAM for right-hand and left-hand circularly polarized optical vortices with the topological charges plus and minus 2. Note that two incoming optical vortices stay the same after all transformations in the sandwich. So if the sign of circular polarization of incoming optical vortex coincides with its topological charge, output optical vortex has the same polarization and topological charge as the input optical vortex. Otherwise, signs of the circular polarization and topological charge are changed. Obtained results allow one to show that 2-qubit quantum logic gate swap can be implemented in the sandwich MAM. Gate swap has 2 inputs and 2 outputs. In truth table shown here, A and B denote a signal as the input, A prime and B prime are at the output. The right-hand table describes transformations of optical vortices in sandwich MAM, assuming that the right circular polarization and positive sign of the topological charge correspond to the logical unity. We found that the sandwich MAM implements the operation of swap gate. Moreover, we obtained non-trivial result for the system of only 2 fibers, multi-helical and anisotropic fiber. At established length of these fibers, the incoming circular polarized vortices are transformed on the output as shown in this slide. It turned out that such implement a logic element for optical vortices, which is equivalent to the operation of 2 fundamental quantum logic gates, swap and C0, which the truth table is depicted right here. To conclude, I'd like to note the main results. Transformations of circularly polarized optical vortices in the sandwich MAM are shown. Parameters of twisted anisotropic and multi-helical fibers in the system for the high-efficient vortex transformation are obtained. All fiber-efficient implementation of fundamental quantum gate swap in the sandwich MAM is offered. It is found that the logic element, which is equivalent to the operation of two fundamental quantum logic gates swap and CNOT, can be implemented in the system of multi-helical and anisotropic optical fibers. Thanks for your attention.